In this video, we're going to demonstrate the basic idea of an expert elicitation for a probabilistic value. We'll begin this demonstration with a very simple model that shows you what the output of an elicitation might look like. For this exercise, we're not going to worry with the details of how to formulate the questions or any of the technical details you're learning in this module. This is a simple commuter model. We want to know how long it takes you to get to work in the morning and what that time costs you. We're going to assume that each minute that you spend commuting is worth 25 cents to you. So we'll develop a model that estimates the total cost of a random commute for you. This will be done by multiplying the minutes of commute time, which is not yet complete, times the cost per minute for the total cost. We want to see the distribution of commute cost for you using the route that you take right now. Then we're going to assume a new road is being built that will shorten your commute time. And we want to see the distribution of commute cost for that future commute as well. So let's begin with the current commute. This is something that we have information about and a great deal of experience with. But if you're like me, you will not have any hard data on your commute time. So we can estimate your commute time by estimating the minimum, most likely, and maximum time it can take you to commute. Estimating minimums and maximums is actually very tricky, but we're going to ignore the messy details of that reality for now as well. I'm the expert on my commute, so my minimum commute time, I'm saying that is about 22 minutes. The most common commute time, or the mode, is 30 minutes. The maximum commute time, one time it took me almost 2 hours during the snow, so I'm going to put 120 minutes in here, and I'm going to use 2 hours as the maximum commute time. Using some non-parametric distributions, we can generate some commute time distributions. All the distributions here return their expected values. Notice that most of them are too high, higher than our most likely value. Let's take a look at the triangle. We go to the At-Risk tab, define distributions to have a look, and we see this triangle makes those long commute times far too likely. Most of the commute times are down here under 40 minutes, and you can see there's a great deal of the triangle over here, and that just doesn't make sense. When I move to the PERT, we have a similar situation. Those times over 40 minutes are far too likely. As a matter of fact, if I get a general idea, over half of them take more than 40 minutes, and that's not accurate. We could also define a uniform distribution, and we see that is equally unlikely. Here, if I grab my delimiter over here, I see far too many take too much time. So what I have done is I've used a beta general here. I used the minimum and the maximum from our data, and then playing with the parameters alpha 1 and alpha 2, I shaped this distribution so that it's a little bit more realistic. Instead of having 80% of the commutes over 40 minutes, I'm seeing about 1 in 5, and that's probably a lot more likely. You also notice that the mode is 29. That's very close to the 30 that we had. So I'm happy with that, and I'm going to use that distribution. So if you look down here, you'll see this number is copied here, times 25 cents. Gives me, for this particular commute, the value of my time was $8.56. Okay? When it comes to estimating times for the new road, we have a different situation because we have no data. This is a situation that's never existed before. For the sake of this exercise, we're going to assume this is a very sensitive project, and this is our most sensitive variable. So we'll do a probability elicitation one-on-one with an expert, and I'll be the first expert once again. we usually begin by bounding the uncertainty. So I'm going to move over here now, and I'm going to say that with the new road, after a lot of thought, I estimate that the minimum time is going to be 20 minutes, not going to shave too much off of that minimum commute. Excuse me. The maximum time, we do get a significant drop there. I think it's not going to take any more than 65 minutes with the new road in there. A common approach at this point, now that we've bounded the problem with a minimum and a maximum, is to now ask our expert to identify a commute time such that half of all commutes will take more than that time and half will take less than that time. So I'm going to give that a lot of thought, and after a lot of thought, I estimate that that is 25 minutes. So we now have 3 data points. There's a 0% chance it'll be less than 20, so we have 0 and 20, 50% and 25, and we're 100% sure it'll be 65 or less. So now what we're going to do is we're going to work with the interval from 20 to 25. And we're going to ask our expert to identify a commute time such that half of all the commutes in that range are more than that and half are less than that. And after giving that a lot of thought, I estimate that to be 24 minutes. So this point yields a 4th data point, 0.25 or 25% and 24 minutes. Next, we're going to work with the interval from 25 to 65. And we're going to ask our expert to identify a commute time such that half of all commutes are more than that and half are less. And this time our expert says 40 minutes. I now have enough points to define the cumulative distribution that you see here. So if we pull this up, you will see that I have used the data that were input here to derive this very irregularly shaped cumulative distribution. Notice that we didn't have to resort to the use of any of the above non-parametric distributions, although we easily could have done so, because we have a minimum, a maximum, and even though we don't have the mode, we have the 50th percentile or the median value. Eliciting our experts' knowledge of the commute, the vehicle they use, the local weather, local driver skills, and so on, we can represent our experts' subjective beliefs without assuming any special shape for them. They just are what they are. And here's what they are. This distribution here has been copied down. So for this particular commute, we see 32.875 times 25 cents, and that's an $8.22 expenditure of our time. Let's run a quick simulation and compare the results. We'll do 5,000 iterations. Let's put our cursor here and begin. So that didn't take very long, and you see the statistics here. It's between $5.51 and $19.47 of your time. Now we're going to overlay a graph, and I'm going to say put this on the same. And you can see how that red distribution has shifted relatively far to the left. And the possibilities of dollar values in this range are far less than they were before. Before we leave this exercise, let's have a look over here. This is where we've listed our elicited information, and we're going to compare it with the estimates of another expert who lives in your house and makes the same commute. Clearly, the two of you have some differences of opinion about the effectiveness of this new route. So how are we going to handle these differences? There are many ways to do this. One is to just use both distributions in a sensitivity analysis to see if the differences are significant. A common approach is to give equal weight to both experts and just average the values. If one expert is considered more knowledgeable or better calibrated, then more sophisticated methods like Cook's classical method are available. Notice that for that very first distribution that we used down here, we didn't have to do an expert elicitation. We had some data, we had some non-parametric distributions, and we used the information that we had, we plugged it into those and came up with a distribution. Most of your work in risk assessment models is likely to be using that sort of expert judgment. And we would like to contrast that with the formal process that we went through here by eliciting very specific values. Using a very explicit formal process for eliciting these values is a bit different than expert judgment. If you've got any questions, please feel free to ask them in class.